Before we dig too deep into binary numbers, I want to be clear about why we care and to what extent we care. We care about binary numbers because they're how computers represent numbers internally. Computers only understand two things, on and off. We represent on with a 1 and off with a 0, and when you're limiting yourself to just 2 digits rather than the usual 10 digits, what you get is a binary number. Now, we care about this from a numerical analysis perspective because the binary representation puts limitations on what computers can do, in particular when it comes to arithmetic. So to understand those limitations, you first have to have some understanding of binary numbers and how they work. Before we dig into binary numbers, I want to take a look at decimal numbers. Right? When we see a number like 1,432,051, what does that mean? Well, the decimal system is what's called a positional system. What that means is that the position of an individual digit, like the 3 in my number here, within the bigger number tells you something about how much it represents. And in each digit represents a power of 10. For example, the 1 out there at the left-hand side represents 1 10 to the 6th, or 1 million. The 4 represents 4 10 to the 5ths, 3 10 to the 4ths, 2 10 to the 3rds, and so on, all the way down to 1 10 to the 0. 1 10 to the 0 is just 1, so that's 1 unit. So to get the original number, all I would do is multiply each digit by the power of 10 that it represents and add those values together. So if I do 1 times 10 to the 6th plus 4 times 10 to the 5th plus 3 times 10 to the 4th and so on, all the way out to 1 times 10 to the 0, the result would be 1,432,051. Now, there's nothing magical about that number 10. We could use any number, any positive, any non-negative integer, any positive integer that suits us for the base. In particular, we could do this with a 2. If we do this with a 2, we get a binary number. Right? Now, remember what I mentioned this briefly on the last slide, but to be clear, a decimal or a base 10 number has 10 possible digits we can use, 0 through 9. A binary number, on the other hand, has only 2 digits we can use, a 0 and a 1, and that's it. So if I wanted to take a number like 1001101 in binary and convert that to decimal, I'm going to do the exact same thing I do with my decimal number. Each of these digits represents an increasing power of 2. So the first digit represents 2 to the 0, the second digit 2 to the first, 2 to the second, and so on. So to do my conversion, I'm going to do this. I'm going to take 1 times 10 to the 1 to 10. I slipped into decimal, right? 1 times 2 to the 6th, and that gives me this part. Then I'm going to do 0 times 2 to the 5th, plus 0 times 2 to the 4th, and so on, all the way down to the end. And if we add all of those numbers up, we get 77. So 77 would be the decimal equivalent of this binary number. And the way I would write this, I would write it this way. 1001101, that's the decimal, the binary number. And notice how I put this little 2 down here. Right, that little subscript 2 tells me that this is not a decimal number, it's a binary number. And that binary number is equal to the decimal number, 77. All right, so if I give you a binary number, that's how you would go about converting it to a decimal number. Right, so what if we want to go the other way around? Right, if we want to go the other way around and take a decimal number, like 250, and convert it to binary, well, there are a couple of ways you can do this. And again, I'm kind of focusing on this from a numerical analysis perspective. We just want the answer, right? So the quickest way to me to do this is a procedure, an algorithm, if you will, that just involves repeatedly dividing by 2 and keeping track of the remainders. Right, so what I'm going to do is I'm going to take 250 divided by 2, and that equals 125 with a remainder of 0. Now I'm going to do this. I'm going to take that 125 and do this again. 125 divided by 2 is 62 with a remainder of 1. And so on. We're going to have to do this several times. 62 divided by 2, 31 divided by 2, so on, all the way down until we get to 0. When we get to 0, we're finished. And our answer, the binary equivalent of 250, is going to be in those remainders. Right? All I'm going to do is I'm going to take those remainders, I'm going to read from the bottom up to the top, and that gives me my binary number. Right? So 250 is equal to 1, 1, 1, 1, 1, 0, 1, 0. You notice I put the little 2 down there for the subscript, so it's clear that that right-hand side is a binary number. Okay, so that's the basic back and forth conversion, all right, between these two systems. So in the next lecture, we're going to talk a little bit about doing arithmetic with binary numbers, because that's going to be a key element in the later conversations we're going to have about those limitations I mentioned.